Okay, so I think we can start now. Hope my screen is visible and I am loud and clear. If there is any problem, please let me know. Uh, so my name is Shutanu Sadhukan. I am as usual again present in your live interactive session. I am a PMRF student of IIT Bombay and a teaching assistant for NPTEL. I am your facilitator for the uh, live interactive session of third week for the NPTEL course code AR18. And the title of the course is Urban Utilities Planning, Water Supply, Sanitation and Drainage. Originally instructed by Dr. Debobrotin Pandit, who is a professor of IIT Kharagpur at the Department of Architecture and Regional Planning. Hope you have watched SAT's third week's lecture. And also, I hope you have watched whatever we have discussed in the last 2 weeks, either the recordings or the you have gone through the slides, if not recording, I hope. So I see some of you are new. Let's see. Daljit has attended. Shomdeep also has attended, I think. So Deepi, Surekha, and Aruna, you three are attending for the first time, I guess, or you are there in the first class. Okay. You can unmute and speak.
We had 2 classes, sir.
Okay, we attend.
Yes.
Okay, maybe for the entire period of time you might not have present. That's why I got a bit confused. It's okay, no issues. So even if some of you are not there, you can again go back to the slides or recording. You can watch. Okay, so we'll start. Now, where are we? We have completed 2 weeks. We are at the third week, 11th August. Now, there is upcoming your Independence Day. So, Independence Day is at what day? It is on Thursday. Okay. So, next week it is. Now, we'll today actually these links I guess you have gone through. This is the recording link where all the recordings are uploaded. Also, this is the Excel sheet where the other TA who is taking the class in Tuesday, those are also uploaded here. The slides are uploaded in this Google Drive link. You are highly encouraged to give feedbacks for the interactive sessions, and if you have any further question, even after the class, and also if you have any question for professor's lectures, you can join in the discussion forum and ask questions there. Okay, so today's class we will start with a concept which we studied in our school level. That is, if you had science, especially chemistry in class 2 level, that is in your 11 and 12th class, then you will be able to remember. If you didn't have, then you might not remember. Okay, so we'll start with a problem with this concept. Shondeep has left. Okay, so okay, rejoined. So what are these three things? These three are basically concentrations of solution, different forms to express the concentration of solutions. So molarity is defined as the moles of solute per liters of solution. Unit is naturally moles per liter, and the symbol with which it is denoted, it is capital M. Molarity is expressed as the moles of solute per kg of solvent. The symbol is small m. Unit with which it is defined is moles per kg. Can anyone tell me what is normality? No one? Okay. So I'll again refresh the concept. So normality is basically gram equivalence of solute per volume of solution in liter, which is nothing but equals to mass of solute in gram into 1000 divided by equivalent mass of volume of solution in ml. Now, as we are studying water science, so what will be there in case of water? So you see, in case of water, the density is generally dependent on temperature and pressure, but in STP, which is called as standard temperature and pressure, the density of water is basically 1000 kg per meter cube or 1 gram per centimeter cube, right? So if the solution is very dilute, then you can see the molarity will almost be equal to molality, right? Because if the solution is dilute, then the uh, kg then it will be basically 1 kg per liter will be the density of the water if the solution is very dilute. So then the molality will approximately equals to molality. But if the solution is not dilute, then it will not be equal, right? For in case of water only at standard temperature or pressure, it is not true for other solvents. And in case of normality, you can understand the definition, I guess. Do you have any doubt? Then you can ask. Otherwise, we'll proceed to our problem based on this concept. Okay, now I'll give you an example. If you consider calcium carbonate, which is a bivalent salt which causes hardness in water. So, in case of calcium carbonate, the weight of calcium carbonate is something like uh, the atomic weight of calcium, that is 40, plus atomic weight of carbon, that is 12, plus 3 into oxygen, which is 48. So 52 plus 48, which gives you 100. It is the molecular weight of calcium carbonate. Yeah. Now for this compound, this calcium carbonate, if you put it into water, the amount of calcium carbonate that is getting dissolved in water gets dissociated into two parts. One is called as the cation and another one is called as the anion. And the charge, that is the uh, the the plus or minus sign that is there with the calcium or carbonate ion, that denotes what is cation and what is anion. And you can see, based on the cation, that is calcium, there is 2 charge, plus 2 charge, and carbonate, that is minus 2 charge. So the valency becomes 2. If you want to calculate the normality of the calcium carbonate in water, then you have to get the equivalent mass of the calcium carbonate. How can you get the equivalent mass of calcium carbonate? The answer is with the help of valency. Okay, so how can you get the equivalent weight or equivalent mass? That is, though weight and mass are not equal, but here in this case we are considering it to be equal. So it is W of CaCO3 equals to normal mass, that is the 100 which we have calculated, divided by its valency in water, which is nothing but 2 in this case. So it will be 100 by 2 equals to 50. So let's say you are given 200 grams of calcium carbonate in water as a solution. Entirely, it has been heated to certain temperature that the entire component has been dissolved into the water. Then what will be the normality? of that calcium carbonate solution in water. You have to calculate in this way. So the mass of the solute, which has been given to you as 400, you have to divide it with 50, which is nothing but 4. No, not 4. So let's say it is 200. Then divided by 50, it gives you 2 into 1000 divided by volume of the solution. Within whatever amount of solvent you have, the amount of calcium carbonate has been dissolved, that you have to take into account in order to calculate the normality. Hope I guess the concept is clear. The molarity, normality, and molality, all these three concepts is clear enough so that you can solve the next problem, where the concentration of calcium carbonate is given as 250 milligram per liter. Based on that, you have to calculate the following. Number one is concentration in ppm. Number two is the equivalent concentration in milli equivalent per liter. Number three is the concentration is ppb, and number four is the molar concentration in millimolar. Okay. So as I have told in earlier classes, how you determine the units. The if you attach with anything, the term milli, that means 10 to the minus 3. Micro means 10 to the minus 6. Pico means 10 to the minus 12. Nano means 10 to the minus 9. And femto means 10 to the minus 15. I have discussed these things in the class. So you should be able to and parts per million, parts per billion. So what does this million and billion means? The million means 10 to the power 6 and billion means probably 10 to the power 12, I guess. একক দশক শতক হাজার অযুত লক্ষ নিযুত কোটি. Yeah, I guess 10 to the power 6 means million. Yeah, it is 10 lakhs. 10 to the power 5, that means 10 to the power 6. That is the million. Parts per million means how much within 10 to the power 6. And parts per concentration means within 10 to the power 6, that is the unit of gram. So 10 to the power 6, whatever the unit of mass, that will be applicable. And parts per billion means within 10 to the power 12. That's all. So this thing you have to calculate. You can take a copy and you can just do the work there, and you can post the answer in the chat box. I will wait for 2 minutes. If you have got any questions, or if you have not understood the concept that I discussed, that I just discussed earlier, then you can ask. So you can see here molarity and molality has not been asked because it is not yet covered in your syllabus. So only the basic concepts like concentration you have to calculate. These units are important when you are checking the water quality in terms of several parameters. Let's say hardness, just like someone asked in the first, someone asked question in the first class, that how do you calculate these things? What are the quality parameters based on different standards like IS standards, German standards, that is DIN standard, American Society for Testing Material ASTM standard is there. There are also ANSI standard, American National Standard Institute, I guess. There are API standard, American Petroleum Institute. There are also Indian standards like BIS. There is BT standard. So many standards are there for the water quality measurement, and many other things like water management also. What it is called as water stewardship, where you have to balance the water that is coming inside the plant and that is going outside the plant, outside of the plant, and how much you are recycling. All those things comes there. That is basically GRI standard. I think it is a German standard under which it is done, and also ISO standards are there, which is widely acceptable all over the world. So all of these standards you will see they are the units are represented like this way: ppm, ppb. This thing you will come across if you are working in an industry, in a water treatment, water sanitation planning industry. If you are working there, you will come across with these kinds of standards. So it is almost 2 minutes is over, 3 minutes is over. Nobody is able to give answer in any. Uh, okay, so I'll proceed with the solution.
Sir, apology for today. Actually, I'm traveling today, so that's why only listening your sessions
Okay,
carefully, sir.
okay, no issues, no issues, no problem. Yeah, no issues. So because this session is not graded, so even if you are not able to answer, no issues. But yeah, if you are there, yes, stably sitting in your home, then you should try. Yeah, otherwise no problem. No issues with that. So the solution goes like this: 1 ppm means 1 milligram per liter. Okay, as I told earlier, here what they have told, it is sorry, I forgot to mention here. So the concentration of calcium carbonate is 250 milligram per liter in aqueous solution, that is within water. So if that is water, then 1 liter means the 1 liter is equivalent to, and 1 ppm is very dilute. So that means 1 liter is equivalent to 1 kg. So 1 milligram per 1 kg means what? 1 gram per 10 to the power 6 gram. That means 1 parts per million. Do you understand why 1 ppm means 1 milligram per liter? So the concentration in ppm will be nothing but 250 milligram per liter. That means 250 ppm only. If you have to express the milligram per liter into ppm, it will be simply 250. There will be no change. The units are same in case of dilute aqueous solution. Now, molar mass of calcium carbonate, while discussing the concept of molarity, molality, and normality, we told that the molar mass of calcium carbonate is 100 gram. How did we calculate? I hope there is no doubt. How we will calculate the equivalent weight? This also again we discussed. It is nothing but 50 gram per equivalent. So it is nothing but your the total molar mass divided by the valency of calcium carbonate aqueous solution, which is nothing but 2. So it gives you 100 by 2 equals to 50. Now, what are the data given? Let's say concentration is given as, only this data is given, 250 milligram per liter, which is nothing but 0.25 gram per liter, right? So this many grams within 1 liter of solution. That means how many equivalent? So to determine that, you have to divide this 0.25 with this 50. So 0.25 divided by 50. Gram gets cancelled out. It becomes equivalents per liter. So unit becomes 0.25 by 50 equals to 0.005 equivalents per liter, which is nothing but 5 into 10 to the power minus 3 equivalent per liter. Now 10 to the power minus 3 means milli. That means 5 milli equivalents per liter. Okay, so if you are asked to calculate the equivalent concentration in milli equivalents per liter, then it will be 5. Hope it is clear. If any doubt, you can ask. So I didn't understand that. Please repeat that. You can tell. Okay, now next is the concentration is parts per billion. So this is nothing. 1 ppm means 1000 ppb, because one is 10 to the power 6 and another one is 10 to the power minus 12. So billion means 10 to the power 12, million means 10 to the power 6. Per million means minus 10 to the power minus 6, per billion means 10 to the power minus 12. Sorry, not 12. It will be 10 to the power 9. So billion means 10 to the power 9, million means 10 to the power 6. So the difference is 1000. That means 1 per ppm equals to 1000 ppb. Am I right? Yeah. So yes, right. That means per billion means what? This per thing means this is in the denominator. If you are increasing the denominator, then the numerator should also increase. So that's why 1 ppm equals to 1000 ppb. So if you are asked the concentration in ppb, already ppm is calculated 250, just multiply it with 1000. So it becomes 2,50,000 ppb. Simple. Now the molar concentration in millimoles. Millimolar. So how to calculate that? 1 mole means 100 gram. 1 millimole means, so you understand the concept of molar mass, right? Molar mass means uh, weight per 1 mole. So 1 millimole means 10 to the power minus 3 mole. 1 millimolar means 10 to the minus 3 molar. And the term molar means moles per liter. That means 10 to the minus 3 moles per liter. Hope it is clear. So that means if you want to calculate the concentration in millimolar, it becomes 2.5. Any doubt? You can see that within 1 liter of solution, there is 250 milligram of calcium carbonate. Right. Now 250 milligram of calcium carbonate, if you divide it with 100 gram, that gives you 2.5 moles per liter. Right. Now what you can see here, they have given the unit in milligrams, not grams. So if you divide it with 100, it will become 2.5 millimole, not mole, which is also present within 1 liter. So that means molar. 1 molar means 1 mole per liter. 1 millimolar means 1 millimole per liter. That's why it is 2.5. Hope it is clear. If any doubt, you can ask. Now, next MCQ is, which one of the following statements is correct regarding the location of surface water intakes? Option A is, quantity of the water available is not important in the planning of locations of the intakes. Option B is, intakes should have sufficient self weights in order to prevent upthrust of water current. Option C is, intakes to be constructed close enough to the navigation channels. Option D is, intakes to be constructed close to sewage disposal site. Previously, nobody was able to calculate the answer of problem, but now it is expected you can type the option in the chat box. Correct answer. Those of you who are stable, who are sitting in a stable manner in your home. Shomdeep has left, I think. Issues. So what is intake water? So you can see, I told you about the ZLD concept, right? Where you cannot throw any water. The entire water that is you are using inside a plant, you have to recycle it back. Uh, so this is called as a zero liquid discharge, where you are not discouraging any water. Even if in that case, you can discharge water in gaseous form. or there will be losses of water. There will be seepage from the pipeline into the environment. There will be cooling towers to cool down. Maybe not also in industries. Even if in case of if you have gone to big hospitals, there you might have also seen centralized air condition, right? To maintain that centralized air condition, that is not entirely electrically driven. There will be a cooling tower outside of that big hospital, or maybe at the rooftop, to cool down the water which is being used uh, for as a chilling water for your centralized AC. Okay, so in that case also, water leaves the system in the form of gas or vapor, whatever you like to say it. So, but a certain amount of water that needs to be circulated in the system. So that's why makeup water is taken. So for the purpose of taking makeup water, actually, you have to design water intake. So the question is, uh, what should be the design? It is based on the design aspect, I guess. Yeah. Okay, so nobody is able to answer. I'll proceed with the answer. You can see the intakes to be constructed close to sewage disposal site. It is not at all true. So if you design that intake in sewage disposal site, natural bacteria will not get the enough retention time to bring down the BOD and COD level of the water into its natural permissible level. So that's why it is not recommended. Even if something happens, the polluted, contaminated water comes out with the sewage and it is not properly treated, what will happen? That contaminated water again will come through your intake. So that's why option D cannot be the answer. What about the other three options? Intake, if you construct it too close to navigation channel, what will happen? It will basically the thrust, not only the up thrust, but also other side thrust. Those things will be high in your pipeline, intake pipeline. So in that case, you have to provide robust support to your pipe. So that means construction cost will be increased. So that's why option C is not permissible. What about the option A and B? Now let's see what is the answer. To 50% I have eliminated. Nobody is still able to answer. Okay. So option B is the correct answer. Intake should have sufficient self weights in order to prevent upthrust of water currents. And quantity of the water available is definitely important. Planning of the location of the intakes. Why? Because entire design will be based on that. So the capacity of the pump, the sizing of the pipeline. You can see in industry you have to maintain, I guess, between 1.5 to 2.5 meter per second of water velocity you have to maintain within the pipeline, I guess. So it is a thumb rule, so that the friction doesn't increase much. There is lesser vibrations in the pipeline. Everything is based on that. So if you take that into account, then you have to design the intake location. You have to think of in such a way that I mean, the water that is coming uh, through the river or in the surface water body, the pipeline is completely dipped into the water. If the pipeline is not completely dipped, what will happen? Air will get sucked in, creating to uh, what is called as your cavitation in pump's impeller, that will damage your pump system or the water pumping system that is there. So option A cannot be true also. Option B is only the correct answer. You can see a water intake is designed here. So our pump is located at an above elevation and water is taken into inside through the suction action of the pump. And you can see why you have to take care of the upthrust. Let's say if the pipe's weight is not sufficient, what will happen? The water will knock at this bending in this position. Are you able to see my cursor? So if the thrust is more, there will be breaking in this, or a pipe may get damaged in this position, right? So that's why the weight of the pipe should be sufficient to balance the upthrust of the water. Also, sometimes what they do, they protect the intake portion of the pipe so that the surroundings river current doesn't affect this region. They separate the portion from which they will take. Actually, there will be gap at the bottom, or there may be at the top, and also the you can see there is a casing around the pipe so that the vibration or thrust of the pipe can be transferred into the structural load to minimize the damage in the pipe, right? So they can provide a casing also. So the upthrust and self weight balance is important for intake. Sometimes they also do something like they can just take the pipe from the bottom, and they can just open up the pipe in this portion from the bottom of the water. Do you understand? So but this is not a good practice, because what will happen, you don't have to take care of the weight and everything of the system, because the soil itself will take care. But the problem is that there are high chances of if you take the intake from bottom to top, there are less chance. But if you take the intake from top to bottom, there are high chances of grits, gravels, dust particles to come inside the pipeline, and that may ultimately damage the impeller of the pump. So that's why that is not very advisable. Here also the chances of foreign particles coming into the pipeline is high, but you can provide a fine screen here at the intake. So that will if you provide the fine screen in top to bottom position, there also what will happen, that the whatever materials that is coming inside the pipe, you have to clean the screen very frequently. But in this case, if you provide the screen, you don't have to clean the screen very frequently, because it is bottom to top direction. So hope it is understandable, because otherwise the gravity is also acting. Here the gravity is not acting. You are only uh, taking the suction force of the pump to draw in the water inside the pipe, right? So now, next MCQ: in which of the below PPP models, PPP means public private partnership, government takes the responsibilities for capital investments and private sector take the responsibilities for operation and efficiency? So government invests in the project, and the private company operates the project. So this is the thing. The options are: option A is management contract model or MC model, option B CC model, that is concession contracts model, option C is BOT model, build own transfer model, option D is BWA model, bulk water augmentation model. There are also other models like BOO, build own operate. Many other models are there. So, but what is the answer you have to tell? You can type in the chat box, or you can unmute and speak. I'll wait for 1 minute. Welcome, Deepthi. No one? It is just a memory based question. Mm, Option C, build on transfer. Okay, we'll see. Option is basically management contract model. It is memory based question. So if you just remember this thing, you will be able to uh, answer. Otherwise, not. So it's just like in if you are just like it defines the battery limit in case of a plant operation. So how much will be under whom if you are collaborating regarding something, uh, some let's say waste from another plant is being utilized as the raw material for another plant. So who will transfer the waste from this plant to that plant? What will be the responsibility of who will be responsible for the carriage the transfer railroad and everything. So everything comes under this type of contracts, which basically defines the battery limits. And in case of joint investments, who will operate that, how many shares of profit will be shared by whom, these things comes into the picture. That's why there are detailed regulatory and legal things are there which are drafted within this type of model frameworks. So when the only the investment is done by the government and the private body takes care for the operations efficiency, it is called as the management contract model. Okay. Now let's come to our next MCQ. Which one among the following sources is not a primary source of water? Option A is river, option B is glacier melts, option C is canals, option D is rainwater. You can type your answer in the chat box. Sorry about that. I think my internet connection was lost. I don't know what just happened. I'll reshare my screen. Hmm. Hope it is visible. You can answer.
Yes, sir.
Yeah. You can have you typed your answer? I have not seen. Okay, I'll go with the answer. So the answer is canal. River, glacier melt, rainwaters, these are all natural sources and primary sources. Canals is secondary sources. Sometimes it is human made. They just cut from the river, or they may join two rivers or two water bodies, two oceans maybe, just like Suez Canal in case of Egypt, the Panama. I think there is one canal which connects the Atlantic Ocean with the Pacific Ocean, right? This Panama. I forgot. Okay, so canal may be natural, maybe human made, but that is mostly secondary source of water. But river, glaciers, melts, and rainwater, which are always natural, that is primary source of water. Okay. Now let's move on to our next MCQ. What is termed as the flow rate of water through an aquifer of unit cross-sectional area under unique hydraulic gradient at 15 degrees centigrade temperature? Can anyone say what is the terminology without seeing the options? Okay, no one, I guess. I'll tell the options. So option A is hydraulic gradient, option B is permeability, option C is groundwater yield, option D is specific gravity. You can type your answer in the chat box. So the definition is flow rate of water through an aquifer of unit cross-sectional area. That means flow rate plus flow rate divided by area. What is it? I have already told. Flow rate plus flow rate divided by unit area means flux, water flux. Water flux through an aquifer under unique hydraulic gradient at temperature of 15 degrees centigrade. This is the definition. Water flux per unit hydraulic gradient at 15 degrees centigrade. What is it? So Daljit is telling us hydraulic gradient, but it is itself the terminology is per unique hydraulic gradient. So it can, option A cannot be the option answer. So it will be either B, C, or D. Okay. So we'll move on to the answer. So water flux of an aquifer is termed as permeability under unique hydraulic gradient at 50 degrees centigrade temperature. So option B is the correct answer. Permeability. Now if you see, as I told in earlier classes, flux means rate per unit cross-sectional area. Right? Now rate means driving force divided by resistance. That I have also told you. Here, what is the driving force? Here, hydraulic gradient is the driving force. Okay. So, hydraulic gradient by resistance is nothing but rate. If you put cross-sectional area as 1, that is unit cross-sectional area, that where then the flux becomes equal to the rate. Now you take the driving force to the left hand side, that is rate or flux divided by the hydraulic gradient. That becomes your 1 by resistance, which is nothing but permeability. So resistance is inversely proportional to permeability here. If you increase the permeability, the resistance decreases. If you decrease the permeability, resistance increases. That means permeability is nothing but the inverse of the rate, inverse of the resistance. This is how it is defined. Okay. So you can if you just think about the term, resistance means what? It is providing it is resisting the water flow. Simple. Now, what is permeability? Means it is aiding the water flow. Permeable. It is making the water to flow more. So naturally they are inversely proportional, right? And mathematics also says it is inversely proportional, right? So now we will move on to our next question. So here one table is given to you. At the left hand side, left hand column, there are mixed ownership companies, debentures, divestitures, management contracts, and concessions. These are the left hand column. These are various forms of PPP, that is public private partnerships, and there are functional methodologies which are given in the right hand column. So which are publicly owned utility, that is managed by private operators. Private operators is responsible for both operation and investments. Option 3 is infrastructure assets are sold to the private investors, and option D is private investor has minority share, operates and shares its financial gain. Now you have to match the particular public-private partnership with its particular functional methodology. You can keep this order same, 1 2 3 4 as same. You can just tell me this correct order of PQRS. I'll wait for 2 minutes for you to figure out. Anyone? No one? Okay. I'll move on to the answer then. So the correct answer is SRPQ. Mixed ownership companies. The functional methodology of mixed ownership company is private investor has minority share, operates and shares is financial gain. Final gain. Divestitures are infrastructure assets which are sold to the private investors. Management contracts, which we actually earlier saw in one of our question, one of our MCQ, we saw that MC is this is one model where publicly owned utility is managed by private operators, because public in that PPP model, all are PPP models. In case of MC model, what happens that government invests, but that is managed. That means operated and efficiency is checked by the private operators. And concession is where private operator is responsible for both operation and investments. Right? Hope it is clear. If any doubt, you can ask. Okay. Now we will move on to our next what? Okay. We'll move on to our next MCQ. So which law states that the rate of laminar flow is directly proportional to the hydraulic gradient and the area of the cross section of the soil? Which law states that? Can anyone say without options? You people are watching Dr. Pundit's lecture or not? Some questions are directly from those lectures. Some are new concepts. Those new concepts are also from +2 level. If you had science in +2 level, you should be able to answer. Maybe you have forgot, no issues. So the options are: option A is Darcy's law, option B is Bernoulli's principle, option C is Archimedes' principle, and option D is Newton's laws of motion. Newton's laws of motion, three laws, all of you know, I guess. What is Archimedes' principle? Archimedes' principle is if you submerge completely or partially one solid inside the water or any fluid, that may be gas also, not only liquid, what will happen? That solid material will feel an upthrust inside the fluid, right? So that upthrust will nullify the weight of the solid. That solid particle should not be dissolved quickly. So if it gets dissolved, it becomes liquid. So or it should not be sublimate. That means not dissolvable in gas, right? Then only you can check and measure if you get sufficient time to measure its weight. So you will feel light, right? Because the upthrust will reduce or completely nullify the weight of the material. The amount of upthrust that will be experienced by that solid material, that means the amount of the force, upthrust force that is called as the buoyancy force. the value or magnitude of the buoyancy will be equal to the weight of the uh, weight of the fluid, which volume is equal to the displacement, equal to the volume that is displaced by the solid particle. So if you are completely submerging the particle, that means you are completely displacing the fluid, that is the displaced fluid volume is equal to the entire submerged volume of the particle. If, let's say if the particle's volume is V and you are partially submerging, let's say you are submerging it with an amount of x fraction, then x into V will be the volume of the displaced fluid. Okay, so x into V into density of the fluid into G, that will be the amount of the upthrust force or buoyancy. If you deduct that amount with its weight W, that will be its reduced weight. That is what Archimedes principle say. Okay, there is a good, very nice mathematical reduction for Archimedes for buoyant forces as per Archimedes principle. Now, what is Bernoulli's principle? Bernoulli's principle, everyone should know. Somebody also told in the first class. It is a balance of mechanical energy, or basically mechanical energy converted into pressure head. P by rho g plus V squared by 2g plus Z. Z is nothing but the elevation of a particular point inside liquid. In our case, it is water. So the energy, if the water is flowing through a pipeline, this is the amount of mechanical energy which should be constant throughout its journey of the water, throughout its journey. So through a particular streamline, you may consider. Streamline is what it is, it's a bit higher concept. We will not go into that. What is streamline and stream tubes? This thing. There are many concept of tensor and everything, matrix. Those things comes into the picture, but we will not go into detail into that. Those Navier-Stokes but a simple Bernoulli's equation is conservation of mechanical energy. So all these three are not related to our question. So what is basically the proportionality of laminar flow rate with the hydraulic gradient and the area of cross sectional of the soil, cross section of the soil. Flow rate is directly proportional to hydraulic gradient and cross sectional area of the soil. It is given by the Darcy's law. Option A is the correct answer. Okay. Now, before moving on to our next MCQ, we will take 5 minutes break. It is 8 o'clock. We will come back at sharp 8:05. You can take a bio break and again come back, or else I am here. You can ask any question. I will wait for 5 minutes. We will restart at 8:05. I forgot to pause the recording. Hope everyone is back. We will restart the recording and yeah. Now, so where are we? Yeah. Hmm. Everyone is back, I guess. Hmm. So our next MCQ is, which one of the following water supply service issues is addressed via demand side management? Option A is operations and maintenance. Option C is consumption intensity modifications. Option C is supply investments, and option D is reduction of the losses and leakages. These are all the water service issues, by issues related to water supply service. Okay. Which one among these issues you can manage by demand side management? That is the question. Supply and demand, there are two sides.
Sir, B.
Consumption intensity modification. Yeah. So you are correct. The answer is consumption intensity modification. Okay. Reduction of losses and leakages, supply investments, operation and maintenance. These are all issues related to the supply side, not the demand side. Okay. So only the consumption intensity modification is related to the demand side management. Now, hope you understand what is supply and demand thing. Now the next thing is again an MCQ. Rainwater collected from roofs can be used most efficiently for the recharge of. Option is storm water. Option B is surface water. Surface water bodies in urban areas. Option C is aquifers, and option D is wastewater treatment plant. Recharge of what? I mean, all of the options that has been given here. Uh,
Sir, A.
Storm water. Okay. So all of the options those are given here. Basically, rainwater collected from rooftops contributes to all of the four options. So all of the four options are contributed by the rainwater collected from rooftops. But the term recharge, that means something else.
Sir, option A.
I will tell. So you see, all of the four options um, they are rainwater is a contributor, but the term recharge is particularly associated with one of the all the four options. Okay, one of the four options. So that's why actually one option will be correct. Otherwise, if the term recharge was not used, all of the four options would be correct, I guess. So let's see what is the answer. Answer is the aquifer. So you can see aquifer is something. Do you know what is aquifer basically? So the thing is that, let's say, we everybody know there is a property of water to come into equal heights. The property of equal height ability or something. I studied it in my mother tongue, in my own language. So it is in Bengali. It is called as Joler Samochchoshilota Dharma. That means there is a tendency of water, if the water body is there and it is connected by something, then if one water body is at a height A and another water body is at height B and they are connected, then what will happen? The and A is higher than the B, then the nature of the top portion, the top surface of the B has a tendency to come at the height of A. So water has a tendency to be equalized in terms of heights, right? So this is the phenomena which we see in case of aquifers. If let's say there is a hill and there is a valley, and at the if you just dig a bore at the top of the hill, you will see water will come up, right? Because water is present there. You can put a shallow tube well there and you can get water at the hilltop. But let's say the entire this entire soil that is inside that is present inside the hilltop and the valley, that is porous. So water that is present in the hill that is connected at the valley region. So if the people who are present in the valley region, they want to, they just want water, what they will do? They don't have to bore a dig. Uh, they don't have to dig a deep bore in the valley region in order to get water. So what they will do? They will just uh, do a very shallow digging at the valley region, and due to the equal height property of the water will just sprinkle out in the valley region. People will just get the water. Why? Because the water is at a higher height in the hilltop, and that is connected through the soil, the porous soil, uh, with the valley region, with the groundwater of the valley region. So it is basically the connection between the groundwater. So we use the recharge term not in case of storm water. We don't say storm water recharge. We don't say recharge of treatment plant. We don't say surface recharge of pond or recharge of river or recharge of lakes in case of urban area. We only use the term recharge with groundwater recharge. So that's why as aquifer is related with the groundwater, that's why uh, the rain water is contributing for the recharge of the groundwater, that is the recharge of the aquifer. If the aquifer is exhausted, that means as you use more and more water, the groundwater level will deplete simply, right? What is the difference between storm water and rainwater? Basically they are basically the same. The rain that is falling, that is called as the rainwater. When the rainwater after falling, that goes into the drain and flows, the rainwater flows through the drain, that is called as the storm water. That's all. So rainwater mixed with dust and all of the surface. So for getting, if rainwater gets polluted with the particles that is present on the surface, then that same rainwater is termed as the storm water. That's all. So if you want, if you are collecting the rainwater and using it, then fine. But if the rainwater becomes storm water, you have to refine it more and more. That's the thing here. So it is no surface water body, nothing. And I hope it is clear. So now we'll move on to our next problem, where a table is given to you and the population of a particular region is given, and how the population is increasing over the years. After 10 years of interval, it is also given. So in 1991 it was 45,000, in 1991 it was 65,000, in 2001 it was 90,000 for a particular region, in 2011 it was 1 lakh and 5,000, in 2021 it was 1 lakh and 30,000. So now, based on the data, based on this based on the data, actually you have to forecast the population of of the year for 2031. So you can see a 10-year interval in each of them. So you have to forecast the population for the year of 2031. And for this forecast, you have to use a method which is called as the incremental increase method. Okay. So have you watched Sad's lecture? Do you remember the formula for incremental increase method? If you remember, I will wait. If you don't remember, I will calculate. So please raise your hand if you remember. If nobody raises hand, then I will proceed with the solution. So you can see incremental increase method formula is something. See if the intervals are same, let's say it is 10 years, it is also 10 years, it is also 10 years, it is also 10 years, and it is also 10 years. Then you will see there will be a term n, small n.
That is the number of decadal population, I guess.
Yes, yes. So the n, in straight away you can consider the n as the number of data points. Here, what is the number of data points? 1, 2, 3, 4, 5, 6. 5 data points are there. You have to calculate the sixth data point. Or maybe if you consider 1971 at the 0th year, then there will be 6 intervals. That's all. So if the so simplified incremental increase formula will be applicable here, whatever Sad discussed in our class. But if let's say if the interval was not same, uh, it is not some interval is 10 years, some interval is of let's say 12 years, some is of 7 or 8 years, then then that formula for incremental increase method you cannot use. So it will be a difficult one which is out of syllabus. So we will not go into that. So just in exam also, we hope that only similar interval thing only will be given. So the year interval among the data points will be same, which is 10 years in our case. So 1981 to 1991, 10 years, 2021 to 2031, 10 years, all the gaps are all same. So you can straight away consider n equals to 6 in our case. Okay, so I guess nobody is raising hand. So I think I should proceed with the solution, right? Nobody remembers the formula. So the detailed solution goes something like this. The population is given. You have to first calculate the increase in each of the 10 years. So within the first 10 years, the increase was 65,000 minus 45,000 equals to 20,000. At the year of 2001, starting from 1991, the increase was 19,000 minus 65,000 equals to 25,000. From 2001 to 2011, within these 10 years, the increase was 1.05 lakhs minus 0.9 lakhs equals to 15,000. From 2011 to 2021, the increase was 25,000, right? So, based on this data, the total increase is 20,000 plus 25,000 plus 15,000 plus 25,000, which is nothing but 85,000. It is the total increase. Now, you have to calculate the average increase, which is nothing but this 85,000 divided by 1, 2, 3, 4, which gives you 21,250. Now, this average increase is termed as small m. This small m is nothing but a term within the incremental increase formula for projecting population. Okay. So the n value I have already told, it is 6 and m value is 2150. These 2 points, these two parameters we have calculated. If you remember the formula, there will be certain other parameters. When we will see the formula, it will be clear to you. Okay. So the next step is that you have to calculate the incremental increase. You can see in the third column, fourth column, basically. Sorry, row. So what is the basically the incremental increase? Incremental is nothing but the difference within the increases. So here there is no increase, here there is nothing. But the difference between the first two increases comes at the year of 2001. That is 25,000 minus 20,000 gives you 5,000. Now, what is the incremental increase for the year of 2011? It is 15,000 minus 25,000. That means minus 10,000. What is the incremental increase for the year of 2021? It is 25,000 minus 15,000. That is 10,000. Hope it is clear. So now you have to calculate the same thing. The total incremental increase and average incremental increase in terms of this data which we just have calculated. So based on this data, the total incremental increase becomes 5,000 minus 10,000 minus 10,000, plus 10,000, which becomes nothing but 5,000. Now average incremental increase is given by these three data. That means summation of the three data is 5,000 divided by 3, which is nothing but 1,667. Now this average incremental increase is termed as K, which is another term that is used to project the population based on incremental increase formula. Okay. So what we have done here, the years are given, the populations are given, we have calculated the increase and we have calculated the incremental increase. Based on the increase, we got the value of M, and based on the incremental increase, we calculated the value of K. Now this M, K and N, these three things will be used to get our solution. Okay. So what is the solution? So incremental increase population for the year of 2031 is given as P2031, which is nothing but equals to, the formula is given like this way, where the intervals are same, and it is based on our syllabus. So the hard things are not there. So it is nothing but P0 plus Mn plus n plus 1 into n by 2 divided by k. This is the formula. This you have to mark off. Okay, there is definition obviously. If you have gone through such lectures or if you have studied it further, then you will basically know why it is like that way. So the the average increase is multiplied with the number of data points directly, and the incremental increase, which is basically K, average incremental increase, it is multiplied with the summation of 1 plus 2 plus 3 plus 4 plus 5 plus 6. So it is nothing but n into n plus 1 by 2. It is, that formula is given like that. Sum of the natural numbers. Okay. So if you have seen the derivation, you will able to understand why it is. So you will get a feel of that. Otherwise, no worries. You just mark up the formula. P0 plus Mn plus n into n plus 1 by 2 into k. Okay. So now P0 means what? It is the population at the 1981, which is our starting data point. That means P0 is P1981 here, plus M into N. M value we calculated, that is the average increase, which is given as 21250. N is, I told you earlier, it is 6. 5 data points plus 1 you have to calculate, so it is 6. Or you may calculate the intervals of 1, 2, 3, 4, 5, 6. There are 6 intervals. So in this way you have to, you can also imagine starting from year 0 as 1971. So it is better to see n as the data points. Now n into n plus 1 by 2 becomes 6 into 6 plus 1 by 2, which is nothing but 6 plus 1 into 3 into K. Okay, which is nothing but equals to P 1981 is nothing but 45,000 plus 21250 into 6 gives you 1,27,500 plus 6 plus 1 gives you 7. 3K means 3 into 5,000 by 3, that is nothing but 5,000. Okay. So this 45,000 plus 1,27,500 gives you 1,72,500 and 7 into 5,000 gives you 35,000. Summing them up, this is the answer. 2,700, 2,07,500. Okay. So this is your answer for incremental increase method. Now with your permission, if you have understood it, I will move on to our next MCQ. So if there is any doubt for the last question, you can ask. Otherwise, we move on to our next MCQ. Okay. So next is treated wastewater from sewage treatment plants, that is STPs, is generally not used for option A, fire hydrants, option B, horticulture, option C, construction activities, and option D is drinking. Which one among the following purpose is not served by sewage treatment plant? You can, this is very easy question. So you can think it as if, yeah,
Sir, it's D.
yeah. Because sewage treatment plant, the water that comes out of it is very crude. There is no RO, UF, these are not there. Membrane treatment generally it's not there. It's just your activated discharge process, then the water just comes out. That's all. So superfine standards that is not maintained in case at the outlet of a sewage treatment plant. That means for drinking purpose, we cannot use the treated wastewater that is coming out of the STP. All of the three things like fire hydrants, you can use that water uh, for the, I mean, for fire fighting, for horticulture also, because agriculture basically, and for construction activities also you can use that. Now a table is given to you again. In the left hand column, there are vegetated soils, permeable pavements, and rain gardens. So these three are recharge structures. You have to match them with their descriptions. Those are given in the right hand column, which is option P is structured landscape reservoirs, option Q is constructed depressions, and option R is allowing runoffs to percolate through paved surfaces. So you can just keep the 1, 2, 3 as same, and you can tell me the order of PQR. You can write in the chat box. I'll wait for 1 minute more, then I'll proceed with the answer. Okay. Now what is able to guess? So the answer is something like this. Vegetated soils is nothing but constructed depressions permeable pavements allow runoffs to percolate through paved surfaces. The term permeable pavement means, like the way I told you about paved area and unpaved area. Unpaved area means where naturally water can pass through. Now, people thought that if, let's say, we make the pavement permeable, we make the pavement with materials which will allow the groundwater recharge. Basically, that will allow the runoffs to percolate through paved surfaces. So that means that becomes a special artificial pavement. That is not regular concrete, uh, regular RCC structures. They are not. So they are called as a permeable pavement, which acts just like unpaved area for groundwater recharge. And rain gardens, they are basically nothing but structured landscape reservoirs. Okay, so QRP is the correct order. Now we'll move on to our next concept. So here we will compare conventional water or wastewater treatment technology. I mean, conventional treatment technologies with the membrane things which are coming nowadays, very advanced. So what are the conventional treatment which are there in place basically? So we will see a few conventional treatment technologies. So one student actually asked one question in one of earlier classes about the oil water treatment. So these all of these basic all of the technologies which we are going to discuss now, especially they are for the oil and grease removal only, and also other some of them are used for other treatments also. So if you see, there is oil water. Oil's density is basically less than the water, and the solids which are mixed with the oil, they become settled at the bottom of the pot. Okay, because the solid density is the highest, then comes the water's density, and oil density is even lesser than the, it is less than 1 gram per cc generally than the water. Sometimes it is when basically people do drilling activities in sea, within the sea, just like in our case, in our country, ONGC is such a company which and Oil India Limited also are these type of companies who do drilling activities to within the sea, offshore, to extract the oil from the uh, from from the ground that is under the seabed. Okay. Now, by digging the ground, when you are extracting that oil, then the oil, there is high chance that the oil gets mixed with the water. So in this way, neither the oil nor the water is usable. So there is you have to separate them out, right? And sometimes also oil spillage occurs. So oil basically remains at the surface as a blanket. So oxygen, sunlight, etc., cannot come easily inside the water, posing a threat to the natural organisms. Those are present inside the water, fishes, fishes, crabs, etc. Phytoplankton, zooplankton. Sometimes what happens, certain types of phytoplanktons and zooplankton which are habituated to grow in lesser oxygen environment or lesser sunlight environment, but uh, they are not um, beneficial to other aquatic lives which are economically beneficial to human beings. Okay, so in that case, what will happen? That particular types of algae, algal bloom will occur. They will basically increase in number in the water. Okay, and the oxygen will get reduced further. In this way, बेसिकली हिंदी में जिसको बोलते हैं कि सट जाएगा पानी, राइट? There is one particular kind of vegetation that is called as water hyacinth. It has been brought from outside of India to India by European settlers and etc. So that's why these type of in Bengali it is called as kochuri pana. This uh, this plant is not this plant is not generated here. It is not originated here. Okay. So basically, it poses a threat to the aquatic lives and also aquatic lives and all. Just like in I stay in IIT Bombay, so at the side of IIT Bombay there is one lake that is called as Poi Lake, and there is a lot of water hyacinth in that lake. And to keep the aquatic life better, that is present inside the lake, there are cleaners, artificial cleaners made by human beings to clean the water hyacinth that is present on the surface of the water. So similarly, if because of the presence of the water hyacinth or because of the presence of the oil, whichever, there is rotten, the water that is present inside the water body that is getting rotten. So this phenomena is called as the eutrophication. Okay, so you have to clean the water. So that's why these conventional wastewater or water treatment technologies are there. Just like in our case, oil cleaning can be done by gravity settlement. So you can see there is a gravity oil water separator. Oily water is coming in, and you are giving it a time to retention for retention. So it is a large vessel. So you can see the flow rate from the pipe will be very high. But once it comes into this large tank, the velocity suddenly drops. So because of that, the oil layer and water layer, the turbulence, if the velocity drops, that means the turbulence gets decreased. If the turbulence gets decreased, that means there is the laminar flow of this oil water mixture. It will naturally get separated. It is naturally form a two layer. You can separate the top layer, top oil layer, and you can separate the bottom oil layer. But you can see in this process, if even if there is some other contaminant other than the oil also, and they are by the help of the density difference, we are, let's say, we are separating them, still there is certain chance that finer particles will be present. Finer means what? Those are basically in the suspension. I have given you the idea of the particle size, which is called as the colloid, which is called as non-dissolved, which is called as the so the particle size, if it is more than 10 to the power minus 5 meter, that is in the milli range, it will settle, it will separate out, easily separate out. If the particle size is in the colloidal range, 10 to the minus 5 to minus 7, it is a bit difficult to separate. It will be in a suspended condition. You have to give a lot of time for it to separate. But if it is less than 10 to the minus 7 even, it is at the nano range, then it is very difficult uh, to separate them, right? So if it is some other solids or something, it will be dissolved in the water. In case of oil particles, it will not easily get separated. So there are phenomena which is called as Stokes law, which determines the settling velocity of these particles inside the water. So if the Stokes law settling velocity is very, let's say, outside of the limit, then easy separations cannot occur. So that's why that is where the conventional technologies don't work. Conventional technologies such as the sewage sludge activated carbon, bentonite clay, vermiculite, perlite, gas wool, ceramic materials, etc., which are based on the absorption or adsorption unit operation. Conventional technologies like hydraulic mixtures, which are based on the rapid mixing. Conventional technologies like hydraulic and mechanical types, which are based on the flocculation unit operation. And based on oil skimming or clarification, the conventional technologies are rectangular or horizontal for segmentation. And you can see the under the remarks, you can see how they will perform in the types of conventional technologies which are based on the adsorption or absorption. Their performance is very poor in recovery of viscous oils. They become quickly saturated with the oil, primarily due to their large surface areas. Okay. The conventional technology like hydraulic mixture, which are based on rapid mixing, they leads to higher percentage of coagulant utilization, which is not economically beneficial. So what are these types of coagulants which are used in case of rapid mixing? In case of hydraulic mixtures, they are like chitosan, dodecyl benzene, sulfonate, polyacrylamide, etc. These concepts will come when you will study the sanitation part. Now comes the flocculation. Here, the energy input is a bit low as compared to the adsorption or rapid mixing operation. Flock formation is better, but flocks may again get broken by hydraulic or mechanical mixing impellers. Okay, so in case of flocculation, there will be impellers, so they will again break the flocculation. Flock means what? If you let's say if you are using coagulation, flocculation means what? If you are using a coagulant, just like uh, citric acid, which is present inside your nimbu, that is melon or lemon. Yeah, lemon. So it is citric acid present. It acts as coagulants or flocculants for milk, just like for the formation of your chana. This is the English of chana. I forgot. However, but you know that, right? You can imagine that what is basically flocculation and coagulation means. In this way, if the particles are very fine, present inside the water, with the help of certain coagulant chemicals, you can make them agglomerate into bigger size of particles so that you can easily separate them. Okay, so this is called as the flocculation. But for the chemical mixing, for the oil mixing of that chemical with the water, you have to use impellers. So whatever the flocks will get formed with the help of impeller, also they will again break. So the you are using the impeller so that the chemical may get mixed with the water very in a very well manner. But again, the impeller is also, it's a kind of trade-off. It is again it is breaking the bigger size of particles is the problem. And lastly, it is the oil schema clarification. It is smaller size, more efficient, but only for the floating oil. The oil that is uh, inside the water, not floating, not at the surface level. So the oil skimming of clarification is not uh, beneficial or efficient for the treatment of water. So here the membrane technologies comes into the picture. So the conventional wastewater treatment technologies for oil water separation like oil skimmers, decanters, example continuous gravity decanters like CGDs, centrifuges, gravity settlement, etc. Those occur on the those work on the principle of density difference between two fluids are relatively slower and cannot separate finer droplets of oil from water at ppm level caused by presence of surfactant molecules. That's why state-of-the-art ultra nanofiltration membrane technologies are the most efficient and effective ones to perform industrial oily wastewater purifications, where the pollutions present are very complex in nature and are very promising to meet the future industrial requirements in obeying environmental norms, which are constantly becoming stringent day by day. Okay, this is why the membrane technologies are performed. So now I will introduce a bit about. Sorry, my connection was again gone. I don't know from where you people missed. Just wait. Let me check the connection. Yeah, it is there. So please, I don't know which slide was missed. Just wait. So did I go through this slide? I mean, are you be able to attend this slide or not?
Sir, this state of art has been gone, sir. It has been explained.
Okay, you came across this slide, right? I mean,
Sir, we crossed this slide.
okay. So this is nothing but explaining why membrane technology is better than the conventional technologies for the water treatment. So I am just giving you a bit introduction because we will solve one problem based on this concept. So membrane processes are nothing but it is my expertise area at IIT Bombay basically. So that's why I'll solve a problem which is relevant to the water supply part. You are treating the water and supplying based on the capacity or head requirement of that particular city. So to understand that, I will first go with the defined membrane technologies. So defined membrane technologies are MF, UF, NF, and RO. MF means microfiltration, UF means ultrafiltration, NF means nanofiltration, RO means reverse osmosis. So why their names are different? Because of the pore sizes, pores that is present inside the membrane. Have you heard about the ships? If you are, let's say, um, when some of you are civil engineers, so while constructing some before some construction activities, people take sand, they will mix that with cement, right? So they just do the sieving of the sand so that the larger sand particles gets retained, and the smaller finer sand particles which they actually want to make the cement sand mixture, they comes through the sieves. That's all. The membranes are nothing but sieves. Okay, so sieves have very larger pore size, maybe millimeters, maybe in the order of millimeters, right? That means 10 to the power minus 3 meter. Those are the basically pores of the sieves. Only uh, larger are there. There are a range of sieves ranges basically, so through which the particles whose particle size is less than the pores, they will pass through, right? Similarly, in case of membranes, why the microfiltration is there? Microfiltration means the pores of the membranes are in the micron range. That means 10 to the minus 6 meter. So the particles which are less than 10 to the minus 6, they will pass. The particles size which is more than 10 to the minus 6 meter, that means 1 micron, they will retain. That's why the microfiltration term. The ultrafiltration, why ultrafiltration? The ultra term means 10 to the minus 7, 10 to the minus 8. This, this is the pore size range. So the particle size that is more than 10 to the power minus 7 meter, they will retain. The particle size diameter which is less than 10 to the power minus 8 meter, they will pass through in a very broad sense in case of ultrafiltration. In case of nanofiltration, nano means 10 to the minus 9 meter. So nanofiltration pore size is basically around 10 to the minus 9 meter. So the pore for the particles which is lesser than 10 to the minus 9 meter, that is at the angstrom level, they will pass through. And the particle size which is more than 10 to the 1 nanometer, they will retain. That is the nanofiltration. Reverse osmosis RO means what? RO's pore size ranges at the angstrom level. So the particle size is more than 1 angstrom, it will retain. If the particle size is less than 1 angstrom, like the monovalent salts is also more than 1 angstrom. So everything almost gets retained in case of RO. Only the water molecule size is less than the H2O. This molecule size is less than 1 angstrom. It gets passed. Simple. Okay. So simple concept: MF, UF, NF, and RO. Hope this is clear. So now, based on this concept, you can see the water, monovalent salts, multivalent salts, viruses, everything will pass through the microfiltration. Bacteria, suspiciously, their particle size, their size is basically a particle, they are living beings. So you may consider them as particle. Their size or diameter is more than 10 to the power minus 6 meter or 1 micron. So that's why they will be retained. Virus, it will, if you want to retain viruses, you have to use ultrafiltration. So if there is virus present inside the water and you want to retain them, you have to use the ultrafiltration. If there is no virus, you can safely use microfiltration. Nanofiltration means what? It also retains, along with the ultrafiltration retain thing, it also retains multivalent ions, like the bivalent ions, calcium, magnesium. If you want to remove the hardness from the water, which is caused mostly by the bivalent ions, you have to use the nanofiltration. Okay, but monovalent as there is sodium chloride, which is basically common normal table salts, that will get passed through. If you want to retain everything, just like as if you want to make it distilled water. So you have to use the RO, reverse osmosis. So everything will be written, water will pass through. You may ask question, then why not distillation itself? You can just distill the water, you can just boil the water, everything will get written, and the only the water vapor will pass through, will condensate it, we will use that. Why we are not doing that? That will be very ultra pure water, right? So why you are not doing that? Because it is called as a thermal distillation, and it consumes a lots of amounts of energy to evaporate the water and to cool it down, and to do this process in a very fast, but there will be water demand, you have to meet the demand at the rate of demand, right? So you have to supply the water at a particular rate, and to meet the demand, the amount of energy that you have to use, that is huge. So that's why people use RO. But still, the energy that is there are high pressure pumps are used for these processes. So the energy that goes into running those pumps are higher than all of the other membrane processes like microprecipitation, ultraprecipitation, and nanoprecipitation. Okay, so hope I was able to give you a basic, very brief basic concept on the membrane processes. Now only 10 minutes left. We will solve a problem based on this concept. Okay, so now you can see the microfiltration. There the pressure you have to apply with the help of the pressure pump. It is 0.1 to 3 bars, and the pore size ranges from 0.1 to 5 micrometer. I told you it is around 1 micrometer. For ultrafiltration, the pressure that you have to apply across the membrane for the water to pass through and for bacteria, virus, or suspension solid to retain. If you are sieving something, only gravity acts as the driving force. But here you have to apply pressure to pass the liquid or solution through the membrane. So in case of ultrafiltration, it is 2 to 10 bar, and the uh, pore size, as I told earlier, it is around to 20 nanometer to zero point 0.1 micrometer. 0.1 micrometer means 1 nanometer, I guess, right? No, not 1 nanometer. It is 100 nanometer. 20 nanometer to 100 nanometer, or you can consider 20 nanometer to micron. So that means it is 0.02 micrometer to 0.1 micrometer. It is called the ultrafiltration range. In case of nanofiltration range, the pressure is even higher than the ultrafiltration. It is 5 to 30 bar. As you can see, the pores are getting smaller and smaller. You are requiring more pressure for the liquid to pass through the membrane, right? So for nanovision, it is more than 1 nanometer. The pore size is more than 1 nanometer. RO is it is around the 1 angstrom range. It is 0.1 to 1 nanometer, right? And it is the highest pressure. So the applied pressure is the highest. So the energy consumption is accordingly highest among the all of the four membranes. Okay, so the pressure is 10 to 100 bar. Okay, now based on this concept, we will solve one problem. So I hope you understand the concept of pressure. What is positive pressure, what is negative? Basically absolute pressure cannot be negative. So sometimes if you are considering gauge pressure means what? Absolute pressure minus atmospheric pressure. If you are subtracting atmospheric pressure from absolute pressure, the resultant becomes gauge pressure. So gauge pressure can be negative. If applied pressure is less than the atmospheric pressure, it creates a vacuum or negative pressure. That means the subtraction, if your absolute pressure is less than the absolute pressure, if you subtract the atmospheric pressure, then the gauge pressures become negative. If it is equal to the atmospheric pressure, it is zero. And if you are applying more pressure, the gauge pressure is positive. Simple. But absolute pressure cannot be negative. Absolute pressure starts from zero. So whatever we have stated here, all the pressures, they are bar. They are not bar gauge. If that is gauge pressure, it will be expressed as bar G. It is not there. So it is simple pressure bar. Okay. So now we will see the problem. So the problem is based on demand and supply of water. Now, recommended per capita water supply levels for designing is given. Okay, you can see there are three serial numbers, three recommendations. So the recommendations are nothing but maximum water supply level in LPCD unit, that is liters per capita per day. This is your LPCD. Okay. So there are three recommendations: 70 LPCD, 135 LPCD, 150 LPCD. When will you use 70 LPCD? You will use this level of water supply when towns provide when the towns is provided with piped water supply but without sewerage system. So if the sewerage system is there, then you will not use that. Now for cities provided with piped water supply where sewage system is existing or contemplated, in that case you will use this maximum water supply 135 LPCD. Okay. Now for metropolitan and mega cities provided with piped water supply where sewage system is existing but contemplated, then you will use this 150 as your what? Okay. So then you will use this 150 LPCD. Okay. So now based on these three recommendations, we have to solve this problem on water on demand and supply of water. So type of the city is given to you, where the city is provided with piped water supply where sewerage system is existing. Population for a community is given as 8,000. Source of the water is given as surface water. Characteristics of water to be treated as only suspended and bacterial impurities is present inside the water. Number of working hours of the treatment plant is given as 18. Okay. Now the question is, first you have to determine the total water demand. Second, you have to determine the water to be sent for treatment. And third, you have to determine treatment train with membrane processes. Now, finally, you have to decide the number of modules required if the flow rate per module is 120 liters per hour. This is the question. So, let's go for the solution. Should we solve this problem today or tomorrow? This was the recommendation that we just discussed in our earlier slide. So this is the thing, you have to calculate all these three parameters. How much more time are you willing to give me? So it will take 5 or 10 minutes more if we are going to solve this problem. Otherwise we may solve it in our next class also, whichever you prefer. What do you say? Please raise your hand if you uh, want me to solve in this class. Okay. So nobody is willing to solve in this class, I guess. Everybody is exhausted. So it is better if we solve it in our next session. Okay. Oh, somebody has raised hand. Okay, let me see how many more slides are there for solving this problem only. It will take around 10 slides. So I am also not willing to solve this problem. We'll solve this in our next session. Okay. We'll start our next session uh, based on this problem. This is a design problem completely at par with what is what water supply, water treatment supply drainage means. It is entirely an urban system. It's very relevant, I think. So we'll start our next class with this problem, and we'll end our this session within 1 minute. I'll stop the recording. What is it? Yeah. So you can ask if you have any question in this class. Otherwise, we'll end the session. Okay. Okay, I guess no question is there.